All right, number systems. So let's go ahead and start with the natural numbers. Give it a quick definition. Set of natural numbers. And I'm just going to style it a little bit, this key phrase. And font weight, bold. Great. Okay, so what we're going to be concerned about primarily here is how to mark up in MathML the following set theoretic notation. All right. So let's just give the sort of standard context. So the set n of natural numbers is unbounded. Okay, it's an infinite set for any natural number n. We call m a factor or a divisor of n. If there's another natural number k such that n equals m times k. Great. And let's give these guys, these key terms, some style. Okay. All right, so there we go. So the set n of natural numbers is unbounded. For any natural number n, we call m a factor of n. We call it m a factor or a divisor of n if there's another natural number k such that n equals m times k. Great. All right, so next what we want to do is just sort of explore how we might write this definition here, this set theoretic notation in MathML. Okay, so we'll do that in the form of code block. So we're dealing with MathML. We're going to give a definition, the natural numbers, displaying it in line. Okay. All right, and the first character to contend with is going to be the double struct capital N, and we're going to give that in the form of a MathML indicator, so math indicator. Its name is, of course, as stated, double struct capital N. Okay, and its HTML entity value is 8469. Happen to just have that handy. Next character is going to be what MathML considers to be an operator, the operator equals. I tend to think of equals as more of a functor. Okay, so I'll say more about that later. So the attributive annotation that I use here is verbal functor. And by verbal, I don't mean verbal in terms of verbalized. I mean verbal as in derived from a verb. Okay? And the reason I think of it as a functor is because a functor is a more general category. Operators are types of functors. So the sort of standard operators are, of course, addition, subtraction, multiplication, division, exponentiation, logarithm, and so on. Right? When those are invoked, the result is a new value. Something has been done to a pair of values or more, a set of values, typically a set of values. Of course, it could be also functions, a set of functions or matrices or something of that nature, polynomials. But when you operate on values such as 1 plus 2, you end up, of course, with the new value 3. To me, equals is somewhat different. Equals is grammatically, if you look up the word equals, right, even in the dictionary, it's categorized as a verb, equals, derived from the word is, to be, from the verb is, to be. So when we're invoking it in an arithmetic statement, let's just say 2 equals 1 plus 1, well, we're really sort of describing in an adjectival sense a Boolean value. Okay, so we end up with something that's true or false. So I like the Boolean designation of functor. I like the, yeah, that's what I like to use as far as attributive annotation for the math operator. All right, so next, let me go with mfenced, which I know is deprecated or being deprecated, in the process of being deprecated in most browsing renderers. But in WebKit Safari, I think 17.1, it is not deprecated and probably won't be deprecated in Safari, so I continue to use it, and I say more about that later on. But to me, mfence is a perfectly fine tag option for parenthesizing values in MathML. Okay, so what do we have inside? We have, of course, before we actually address that, let's just go ahead and finish up this tag here. So we're going to open, with brace, and we're going to close with brace. And even though the default separator for mfenced is comma, there's no harm in explicitly stating that, and it also helps with maintaining a stack structure that's pleasant on the eye, on the programmer's eye. So inside we have some numbers, some values, and what I like to do here is sort of offer some attributive annotation that's meaningful semantically. Okay, so first number is number 1 in the set of natural numbers, and the number 1 is a constant here, of course. I mean, it's not an arithmetic statement as much as or expression as much as it is an element of a set, but it is we'll treat it as a constant, and this constant is an element of the set of natural numbers. It is an element of the set of whole numbers. It is an element of the set of integers. It is an element of the set, oops, see what happened there, of rational numbers. It is an element of the set of real numbers. Okay, and this is a bit more incidental, but we'll use it. The fact that 0 factorial equals 1. Once again, to maintain the code stack structure, the symmetry of this structure. That'll be a common theme that you'll see me employing. All right, so something similar is going to be happening here for the number 2. Once again, it's a constant. Once again, it's an element of the set of natural numbers. Now, it also happens to be an element of the set of primes, right? We'll say more about this later. Once again, an element of the set of whole numbers. Element of the set of integers. Element of the set of rational numbers. And it's an element, element of the set of real numbers in this case, and element of the set of rational numbers. Okay, and of course, what we don't require here is really anything else. We're going to add this character once again to maintain symmetry of structure as best as we can. Okay, and then we just need one more value, and that's the value 3, the number 3, which has the exact same attributive properties as the number 2. It's an element of the set of the naturals, primes, whole numbers, integers. All right, and that should do it. So this code stack right here will render our familiar set theoretic notation for the set of natural numbers. Okay, so we can test this. And we'll do that in 𝗕sc. Make sure it renders, yep, so it renders just fine, exactly the way we would expect it to. Okay. All right, so let's do another. Let's do let's do the prime numbers. Since we're on it. Okay. Very good. So let's just give another definition. Boldface. If the only divisors of a natural number P are 1 and P, where P does not equal 1, then P is said to be prime. And we have another keyword here, so go ahead and stylize it a bit. Okay, great. So if the only divisors of a natural number P are 1 and P, where P does not equal 1, then P is said to be prime. Very good. So similarly to above, let's just go ahead and set up our problem. In this case, double struct capital P, and we'll give the set notation. Lower dots. Perfect. All right. And what's the context that we're considering? Perspicuously, 2 is the only even natural number that is prime. Moreover, every natural number that is prime has exactly 2 factors. Namely 1 and itself. If a natural number n that is not prime, or that is not equal to 1 rather, is not prime, then we say that it is composite. All right, and then all that's left to do really is to work out a code stack that renders this expression here. You just go ahead and copy this guy. So we've worked out what we need. And then we can just make the necessary changes. So it's a definition in this case of the primes. And I'll go ahead and say prime numbers. Double struct capital P is what this character is. The HTML character encoding, entity encoding for the primes happens to be 8473. Great. And the only thing that really changes is we're not dealing with the value of 1, which is not a prime number, but rather we're starting our set at 2 and then working our way up to 5. And that ought to do it. So let's see if we can get this code stack to render this guy. And it does. So there you go. Pretty straightforward MathML solutions for the set theoretic notation for the set of natural numbers, or the definition of the set of natural numbers, and one for the definition of the prime numbers.